to OB. OB is perpendicular to OB. So those two lines are perpendicular to each other. Okay. BD is a tangent line at point C. At a point C. So now, you are asked two questions. First, you must prove that this quadrilateral is a cycle quad. The quadrilateral OECF is a cycle quad. To prove that a quadrilateral is a cycle quad, you need to show that the opposite angles are supplementary angles, meaning that their sum is 180 degrees. And another way to prove quadrilateral is a cycle quad, you need to show that the external angle of a cycle quad is equal to the opposite interior angle. Proof. Okay. Let us prove the first one. So the first one, we need to show that this is a cycle quad. So to show that that one is a cycle quad, so you look at your diagram and you check your diagram and you look which angles that you can find there, right? So the very first angle that you have, it's given to the statement. So the fact that AD is perpendicular to OB, so you see this to OB, meaning that this angle inside here is equal to 90 degrees. So the reason is just given in your statement there. So this is the quadrilateral that we must prove that it is a cycle quad. So the first fact that you have here is that the angle FOE is equal to 90 degrees. The reason is given in your statement, so you know that AD is perpendicular to OB. If two lines are perpendicular to each other, meaning that those two lines are meeting at an angle of at an angle of 90 degrees. Perfect. So all right, so now you quickly check the opposite angle of that one. So the opposite angle of this angle is this one. That is the opposite angle of that shape. So okay, so the opposite angle. So what did you know about this opposite angle? So you know the angle of the semicircle. So if that one is the diameter and it suspends the angle that is equal to 90 degrees in the circumference, so you can just say, okay, ACE is equal to 90 degrees as well. The reason is that the angle of the semicircle. So once you have the diameter there and it suspends the angle that is a right angle in the circumference of the circle. So therefore you can just see that the sum of these two angles is must be must be 180 degrees from the previous statements. Therefore, you may conclude that these two angles are supplementary angles. Therefore, the quadrilateral, this one is a cycloquad. It's a cycloquad. So we done there. So now we do the second proof. This is the first one. So this is the first one. So you done it here. So the second one. So now let's do the second one. The second one. Okay, so you need to prove that this line is equal to that line there. So you already proven that this one is a cycloquad. So now you know the exterior angle of a cycloquad is equal to the opposite interior angle, meaning that, so now you have a triangle here. If you can show that these two angles here are equal, that will mean that these two lines are also equal, because this triangle is an isosceles triangle. So you know the base of an isosceles triangles are equal and the two sides also equal. Okay. All right. So you know this is the exterior angle of this cycloquad. So this exterior angle is equal to that interior angle over there. So you just say the angle BFC, the angle BFC is equal to angle OEC. The reason is the exterior angles of a cycloquad. That is the exterior angle of a cycloquad. Another one is that it's given that these two, it's given that BD is a tangent line. Since this is a tangent line, meaning this would mean that this angle over there is equal to that angle, and also this one is equal to that angle. So the angle BCF is also equal to OEC. The reason is tan chord. Tan chord theorem. So now from these two statements so shows us that these two statements show that these two angles are equal. So BFC is equal to BCE. Right. From the previous, and again from that one is you can just say you have proven that BF is equal to BC. So you done what you were looking for.